Hey students, I know chapter 30 can get a bit tough, and so I thought I'd do a few more examples. As you probably have already seen on the other videos, I did some, examples on the lecture videos, as well as some examples as extra videos for sections 1 and 2. So what I thought I would do is do a list of examples that I think would be educational from chapter 30, but it's section 3 and on to the end of the chapter. I also thought then I would print this up because this is the video lecture, and then number 21 is the one that's the end of chapter 30, and I start doing a bunch of examples. And actually the examples for chapter 30 start on lecture video number 20, but they're really from the first sections of 1 and 2, and then it that continues at the start. So section 3 and beyond begin at 30 minutes. So 30 minutes and 55 seconds. So if you go to video lecture 21, you'll see a bunch of examples. In fact, the examples that I made in my notes here are 23, 28, 31, 38, 41. That's a terrible looking 41. 41, 59, 47, 49, and 67. And so 3 of these, 23, 28, and 29, I had enough time to do in the video lecture. So again, if you want to see those 3 examples, and that's where I would encourage you to get started, is to watch the end, if you haven't already, video lecture 21, and go to this timestamp and watch me do number 23, 28, and then 59. And so then here, I thought I would do these 3 in a video right now, and then these 3 in a follow-up video. I think all 6 of them in one video might be a little too much and too long here. And so it'll be take these 9 and put them in 3 groups of 3. So again, for this video, let's do these. And then a video coming out later will be this one. And these are all the magenta ones, I believe. So these are the real hard ones. So I'll save that for a separate video. And then these are the ones I already did in the video lecture. All right. So with that in mind, let's jump to number 31 here. And so I printed up number 31 here. And it says a long cylinder conductor of radius capital R, and so we've got a little picture down here, carries a current I, so here's I, as shown in this figure 30.31. The current density J, however, is not uniform. So that's what makes it a little harder than we did in the other examples, is we don't have a uniform current density over the cross-sectional of the conductor, but is a function of this. And so it looks like it grows with radius. And so if I was plotting the density of the current as a function of R, it would kind of get bigger as we get towards the surface. So very little current in the center here, and then increasing larger as you get out. And a little beyond our studies, but this is a common example of superconductors and some other circuits, that the current density does have this kind of linear distribution, 0 in the middle and getting bigger towards the edge. And so this is a good example. B is just some constant value. Okay. So in my case, the B would then be the slope here of this graph. Find an expression for the magnetic field B at, and then part A says radius R1, which is basically saying inside of the wire. And then B at a distance where R2 is greater than capital R, meaning outside the wire. So, basically find the magnetic field everywhere, both inside and outside. Okay, so I'll give that a try here. Why don't I jump over to my yellow pad here and go, okay, so number 31. And we learned here Ampere's law. That is, if you make an Ampean loop, that is a closed Ampean loop, and you integrate the magnetic field over that path, you get the mu naught, permeability of free space, and then times the current that goes through that Ampean loop. So this is, sections 3 and 4, Ampere's law. So we're going to apply Ampere's law to a non-uniform current. Then, so coming over here, maybe I'll do a little Ampean loop here in blue. And so for the first part, I'm going to just draw a circle. And the Ampean loop is centered at the wire. And of course, this is the kind of the key to Ampere's law, as well as Gauss's law, that you really want to have some matching symmetry here, because you're going to see when we try to do this integral and dot product, there's some symmetry arguments we need to make, or you might even say anti-symmetry argument. But there's my Ampean loop. And in fact, maybe if we want to do a cross section, that could be helpful. And so here's a cross section. So imagine the current coming at you, and here's kind of the center. My Ampean loop is at a radius of little r, because the whole wire has a radius of capital R. Okay, so let's do the part with the dot product first. And so we like to go B ds cosine theta, and then we'll worry about the other side of the equation a little bit later. But this is the important part of our symmetry argument, or our anti-symmetry argument in this case, because if you come back here and you kind of imagine you being microscopic and maybe the magic school bus, and you're inside the wire right here, or even right here, or right here, or right here, but anywhere along this Ampean loop, you will see this current distribution. And so if you could imagine you're standing here looking towards the center, you would have a bunch of current flowing all around you. But my point is, if you went someplace else on the Ampean loop facing the center, you would see exactly the same current distribution. And since it's the current that makes the magnetic field, we could fairly conclude that whatever the magnitude of B is, it must be the same, and therefore a constant value, not everywhere, but along the Ampean loop. And so I can then pull B in front of the integration. And that's the real key to these problems where we're doing Maxwell's equations in integral form, that we take some symmetry arguments. And so that's my first step. And it's an important one too, because if I couldn't make that step, I'm kind of stuck, because of how you're going to do an integral of something you don't know. And so we want to solve for that one. And so we able to argue that it's a constant, at least a constant over that integration path. Not a constant everywhere. In fact, that's hopefully what we will eventually find is the magnetic field everywhere. And we'll see it's not a constant, but at least we'll have a constant over that path. Okay, now this angle is another symmetry or anti-symmetry argument. If I were to draw a line through the center, and imagine then taking this whole wire and flipping it over, you would argue here that, okay, when you flip it over, you get current going in the other direction. The distribution of the current is still the same, but it's just in the other direction. So the argument is, when you flip it, you must get a magnetic field that has the same magnitude, but opposite in direction. So going to the green marker for magnetic fields that we've been using, that means the magnetic field could not be, say, something like this, angled at some angle, say 60 degrees off this line of, again, I'll call it anti-symmetry, because when you flip it, you get the same distribution but opposite in direction. Because when you flip it, you would get this. And that new vector is not the opposite of that one. In fact, it would not be along the line of an anti-symmetry. That was our argument in Gauss's law, that it had to be along a line of symmetry, because when you flip around a line of symmetry, if you end up with the same thing, the vector must be along the line of symmetry. Our argument then goes that it must be perpendicular Now, it doesn't really say whether it is, perpendicular, I'll say up and right or down and left, but it does say it's got to be perpendicular, because if it was up and to the right, when you flip it, you now get the same size and down to the left. And so that's exactly the opposite. So that's why I kind of want to make an important distinction between lines of symmetry and lines of anti-symmetry. And of course, this whole thing has a zillion, technically infinite, number of lines of anti-symmetry. And so the magnetic field, and maybe I'm not doing a good job here because I'm actually drawing the magnetic field outside of the wire. I should be drawing it inside the wire, since that's what we're trying to do in A. But whether A or B, whether inside or outside of the wire, these are lines of anti-symmetry. And so the magnetic field must be in these kind of circular loops, which is the path of our integration. So that would say then that from an anti-symmetry argument, this angle right here needs to be either a 0 or 180 degrees. And of course, notice I'm talking about the angle between the magnetic field and the line I'm integrating, not the magnetic field and the line of anti-symmetry. So I'll say it again, the magnetic field and anti-symmetry is 90 degrees. But what this formula is saying is the magnetic field and the path that you're integrating. So I know I'm doing a circle around the path. That's why I'm doing this anti-symmetry argument to find the direction of the magnetic field. And it turns out that after I study it for a while, I see that the direction of the path and the direction of the magnetic field are in the same direction, or 180 degrees. But if we're talking about, let's just find the magnitude of it, and we can use right-hand rule number 2 in order to get the direction, we could argue here then that let's just take that as a 1, or the negative 1 will ignore the negative part of it. Okay, so then we got just an integral that is around the path, and that's the circumference, and so that's just 2 pi r. Now maybe I should call it r1, since your author made that very clear. Let's refer to the distance, and when it's less than capital R as being inside the wire, as r1. Okay. Well, now another challenging part of this is the other side of the equation. How much current is inside? And inside, hopefully you could come back to the picture and see that if the total current flowing is I, then this smaller circle would incorporate something smaller than I. And so right here, the I inside is going to be something less than the total I. And of course, you can now imagine that how much less would depend, where or what the radius is, the R1 of this Ampian loop. So maybe it would be here. Actually, if it's close to the edge, it'd be almost all the current. And since the current gets really strong towards the surface of the wire, a Ampian loop, halfway is actually just probably about a quarter of the amount of current. So there's some kind of function here we got to deal with. In fact, maybe then I'll kind of jump to a second page, and so I'll go mu naught and then the current inside. But let me do that on another page. Because if I take the current density to be defined as a little bit of current within a little bit of area, and I come back to my picture, which I've drawn pretty heavily on this picture, so maybe I better draw it kind of over here again. And so maybe here's the surface of the wire. And I could maybe think of the here, let me do the Ampian loop. Here's the Ampian loop. Yeah, that blue and black, I should have done a dotted line. Hard to tell the difference. But here's what I'm thinking. I'm thinking that what I can do is take a small little ring, and then another ring, and another ring, and another ring, and another ring. And so, in other words, the current on the inside of that Ampean loop is a sum of the current in each little of these red rings as I add up these red rings. And so I'm going to then use this definition to say, okay, the current density is given by this equation. And so if I let this I represent the current in one of those rings, then A is the area of one of those rings. Now, the area of a ring, maybe if you did the circumference here, I don't know if this would kind of help here, but if I think of this as one of the rings, and I imagine cutting it, then its area would be how long is it, and then times its thickness. And since these are microscopic rings, let me use my calculus to say this is a microscopic thickness to it. And of course, the length is the circumference. So in other words, the area would be the length, 2 pi r, times a thickness of dr. And so I'm going to add them up. And so this would be the current in a ring. So I'll move this to the other side. So this would be the J, the 2 pi r dr, and I add them up, although let me go ahead and replace the summation with the limit as delta r goes to 0. I guess we could call that kind of a delta r and a delta I at first. And delta I is the current in a ring. And then we take the limit as dr goes to 0. So that becomes, or delta r goes to 0. That's why it becomes a dr. And that's why the summation becomes an integration. And then if we use the formula that they gave us that said the current density is not uniform, it would be some constant B times R, and then we got the 2 pi R dr. Now we can actually perform the integral, starting with anything that's a constant. So the B, the 2 pi are all constants, and then we have R squared dr. And we would be adding up from 0 to R1. Right? That's the radius of the Ampean loop. Right, and again, notice I am not adding up all the way to the total capital R. That would give me the total amount. That's probably what I'll do in part B, but I'm not there yet. So let me just call this a B, a 2 pi, and then this would be this R cubed over 3 evaluated from 0 to R1. So that's a B, 2 pi. And I guess I'll put the 3 here, and this will be an R1 cubed. Okay, so let me take that and go back to page 1. So here's page 1, and I'm going to put this then as a B times a 2 pi. And this will be an R1 cubed over 3. Nice. And now, if I simplify this a little bit, the 2 pi's go away, and even one of the R1s go away. And so B becomes mu naught, B magnetic field, mu naught probability of free space times this little b, which we don't have a little number to work with, R1 squared over 3. And they don't give us any numbers, so we can't put an answer in terms of a number, but the general rule is that they give you numbers, you put them in, and then you get an answer in numbers. If they don't give you numbers, then you need to use the symbols that they gave you in the problem. So you don't want to like finish the problem and have like current on the inside. That was not specified in this problem, okay? But little b is, so it's fine to have the answer in terms of little b. And that's what we do. And the constants of nature, that's fine too. Anyway, so there would be the answer to part A. What is the magnetic field inside? Now, we can do all this again, and not much changes here. I'll start with Ampere's law. But as I was touching on already, when you're outside of the wire, so maybe I'll come over back to this page 2 and say, okay, so here was my Ampean loop when I was inside. So this was R1. Now let me do an Ampean loop that we'll call R2, because R2 is, where is R2? Oh, yeah, right in here. R2 in this picture is outside of the wire, okay? And on part B, really, the argument is exactly the same. If you look at what we did here, we would just take this dot product, and then we would argue that everywhere along that Ampean surface, B is a constant. We would imagine ourselves outside, maybe standing here, 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 and here, but no matter where we stand as we look in, it has the same current distribution. And also, the lines of anti-symmetry, meaning that if you took this whole wire and flipped it around, all these anti-symmetry lines would tell us that the magnetic field must be perpendicular to these red lines. And so the green line is the magnetic field. And of course, what we're after in this dot product is the angle between the magnetic field, that's the green lines, and the path, which is the dotted blue line. So they're in the same direction, or 180 degrees. So this is that argument. And so without maybe spending an overwhelming amount of time, this just becomes B times 2 pi R2, exactly the same logic as we did in part A. Now, here's where I guess I kind of have a judgment call to make. Here, I think it would be fair to just say that we could use the symbol I and finish the problem. Actually, maybe I better pause back here. Notice that when I make an Ampean loop that is bigger than the wire itself, then all the current is what goes through on the inside. So for part B, I could say that the current on the inside is equal to the current total. And so that's the step I'm going to make. And that's actually given in the problem. And so since the general rule is to give answers in the symbols that they give you, I think we would be okay to justify I as a given one. It's at least in the picture, and it's also in the wording here of the problem. So I think it's safe to say that this would be a fair answer. Now, I keep saying that because like we did in A, we could write this total current in terms of the current density in B. And so maybe I should do that too, so we have both. But I wouldn't surprise me at all if I look up at the solutions from the author and they have just this, because we don't have numbers, so I can't put any numbers in here. But we do have the same symbols that were given in the problem as in our answer. So I think that's fair. And so maybe he kind of overstated his hand in this problem. And because of that, let me go back to page 2. And if I was doing part B and going through the same logic, I would say, okay, the current on the inside being a summation of a bunch of rings. And so the current in each ring would then be the same logic, this integral of J, and then the area of a ring is 2 pi r dr. Now, the one thing different in part B compared to A is my rings, when I start adding them, I would, back here in this picture, I would add my rings. And last time I stopped when I got to my ambient loop. Now I want to keep going till I get to the edge of the wire. I don't want to keep going all the way, though, to the ambient loop because there really isn't any current out past the wire itself. So in this case, I would stop at the boundary of the wire, not because I hit that first and I ran out of current. Whereas in A, I got to my ambient loop first. So this would be from 0 to capital R. And so that means over here, you'd get a B, a 2 pi, and you'd get a capital R cubed over 3. And now if we go back to page 1 where we wrote this, we could then say that, okay, this would be mu naught over 2 pi R2. And then the current, total current, because the current inside and the current total are the same, would be this B times 2 pi capital R cubed. And that's where it differs, over 3. And we get a little bit to cancel, but not as much as before because our R's are different. See, in A, the R1 was on both sides. Now we have a little different. We have an R2 on this side where we do the ambient loop, but an R where we calculate the current, a capital R. And so this becomes mu naught B R cubed over 3 R2. And so this would be when you're outside. So this is when little r is greater than capital R, and then this is when R is less than capital R. So inside, outside. In fact, you can even see how they match in the sense that when you're on the boundary, if you put in on the boundary here, you put in a capital R, you actually get the same thing when you put a capital R here, because when this is a capital R, one of them cancels, and you just get capital R squared, and that's what you get here when you are at the boundary. So the magnetic field, I guess if I was making a graph versus R, on the inside, it would be quadratic, something like that. And then here, it'd be inverse on the outside, with, again, the peak magnetic field happening on the surface of the wire, which is an important part of our superconductor activities. All right, well, I took probably way too long on that, but hopefully the details helped. Let's try another example. The second one I said I would do is number 38 in this video. And so 38 says that a solenoid that is 10 centimeters in diameter and 75 centimeters long is made from copper wire that has a diameter of 0.1 centimeters with very thin insulation. The wire is round onto a cardboard tube in a single layer with adjacent turns touching each other. Now, maybe we should pause right there and see what they're saying. They're saying you have this wire, and let's see, give me something to wrap around here with here. And so if I take this and I wrap the wire, they're saying you take this copper wire and you get it right up as close as you can. So there's no little opening. Now, they do have some insulation on them, so the current does have to go around the loops. If there wasn't any insulation, that'd be problematic. The current would just, flow across there instead of around the loops there. But this then would be our solenoid. Okay, looking something like that. It says here, what power must be delivered to the solenoid if it is to produce a magnetic field of 8 milliteslas at its center. All right, so we got a couple things going on here, and maybe the first one is to talk about the magnetic field from a solenoid. That's the main part of this chapter before we jump back to other chapters. But we learned here that applying Ampere's law to a solenoid, this is the equation for the magnetic field, where this little n is the number of turns per length. And so the number of loops. And so if I had this, solenoid, I'd count 1, 2, 3, 4. I'd have 4 windings. And so n would be 4. And the given length would be, I'll just call it roughly a centimeter. And so it'd be 4 windings or 4 loops or turns per centimeter, which would come out to be like 400 per meter. Okay? So that's an important piece. And I think they gave me enough information about the geometry to find that. And then I'm going to be able to find the current. And so let me start with this little n in this problem, because when they say the copper wire has a diameter of 0.1 centimeters, they would butt up against each other, and you would get 10 of them, and you would make 1 centimeter, because the diameter of all these is just 1/10 of a centimeter. So you go around 10 times, and it'd be 1 centimeter long. So it'd be, smaller than this. I got 4 for about 1 centimeter. This wire would give me 10. And then we would do that for 75 centimeters. And so each centimeter having 10. And so we're looking at 750 loops that would go along. It would be, a division problem. I have 75 centimeters, and this is the diameter of one of them. So how many times can you put one wire into this length? And 750 seems to be the answer. So we have 750 little loops in a distance of, and I'm going to switch it over to meters, and then this would be 75 meters. And I don't know if how you want to write this. Maybe the easiest thing is to, multiply top and bottom by 100. So here's 100, and then I would move the decimal here. And then the 75 would go into there. And so we're looking at 1,000 turns or loops per meter. In fact, you can imagine that the density has nothing to do with really how long you made it. So we didn't even have to use the whole length of this cylinder. This is the density of it. And you can kind of see that if we had 1 full meter, well, we'd get 10 little loops for 1 centimeter, and then a meter would be 100 of those. So it would be 10 times 100, which is 1,000. So there's our density. And we're trying to make a magnetic field. What was that magnetic field? 8 millitesla. All right, so on this side of the equation, I have, let me just write it as 8 times 10 to the minus 3 for the magnetic field. 4 pi times 10 to the negative 7 for the permeability of free space. 1,000, which I'm just going to write as 10 cubed for the n, and then I get my I. And so this tells us how much current we're going to need in this little solenoid. So why don't I take my 8 times 10 to the negative 3 and divide it by, and it'll be okay. I'm going to just put the 10 to the 3 with the negative 7 and make it a negative 4. And so I can divide that by 4 pi times 10 to the negative 4. And so we're looking at a current of about 6.37 amps. Yay. Okay. And so there's the amount of current. And that's the part that is new this particular chapter. But it's not quite what it says here. It says what power must be delivered. So we need to go back a few chapters. I guess it's back to chapter 27. Was that our first one on circuits? Yeah, where power is current times the voltage, or I squared R, or V squared over R. And I think I'll use this one here because I've already done the I, and then the R, since it's just a copper piece, again, I can go back to chapter 27 and look up the resistivity and the length and all that. So it's going to be straightforward here to get my resistance. Now, I will recall that there is an effect of temperature, and they don't say anything about this solenoid warming up. And so I'm going to take the implication that it's at room temperature, 20 degrees Celsius. So we'll look up the resistivity of copper at room temperature. And I think I remember that, but I better look it up. Reach over and grab my textbook here. But the start of chapter 27, here it is. It's table 2. We had the resistivity. And so for copper, it's 1.7 times 10 to the minus 8. Okay, so 1.7 times 10 to the minus 8. And now we've got the length and the cross-sectional area to deal with. And maybe the, which would be easier to deal with. Well, maybe the cross-sectional area first. So this wire, you know, as they said somewhere in here, it was a tenth, right? Yeah, where the wire diameter is a tenth of a centimeter. And so that means its radius is half a centimeter. Or put 2 zeros, it would be this much in meters. Okay, so this is going to be pi 0.0005. I should just double check that. Let's see. So this would be a centimeter. So this would be a tenth of a centimeter and half of that. Okay. So there's the cross-sectional area. Now, the length of it, since it has to, we'll come back to this little one that we made, how long this is would be the circumference for one loop, and then how many loops do I have? So it's going to be 2 pi r. Now, I want to be careful. This is a different r. Just to be clear, this r was the diameter and the radius of the wire here where the current is flowing. Whereas trying to get the length of the wire and it's wrapped around the solenoid, I need the radius of the solenoid. So don't confuse the radius of the solenoid with the radius of the little tiny wire. And as you can see in the problem, they said the solenoid, they give us the diameter. So that means the radius is 5 centimeters, so 0.05. So 2 pi times the radius of the solenoid would be the length of one loop. And as we said earlier, there would be, let's see, how many? 750 of these. 750. as we go around, and we go 10, make 1 centimeter. And then we have 75 centimeters. All right, so this should give me then the resistance of that wire. And you can see it's pretty long and pretty thin, although it is made out of copper. So kind of curious what this is going to come out to be. So 1.7 times 10 to the negative 8, 2, the pi canceled off, times 0.05 times 750 divided by 0.1235 squared equals. And so we're looking at 5.1 ohms. And so, of course, now to finish the problem, it's I squared R. So this is 6.37 squared, and the R is 5.1. So I already got the radius there, and then the current is that 6.37 squared. And so how about 207 watts? Yay! And so there's our second of our 3 examples for this video. Okay. And let's try 41 before we take a little break and do another video. Let's see here. Here it says a solenoid again. Okay, so a solenoid is 2.5 centimeters in diameter and 30 centimeters long, and has 300 turns and carries 12 amps. Calculate the flux through the surface of a disc that has a radius of 0.5 centimeters, or excuse me, 5 centimeters, and that is positioned perpendicular to it, the axis of the solenoid, as shown in figure. And I printed up this one so we can look at it. Right here. So this is kind of the picture. Here's the solenoid. So current comes in, wraps around, and they gave us all the details of this solenoid. But notice they're saying here that the radius of this solenoid would be 1.25. And so notice here, then they're going to make a disc that is actually bigger than the solenoid. And so that's what they're trying to show here, kind of in this yellow. This disc is bigger, and the solenoid goes through that. So why don't we begin this problem with what we do know about a solenoid? The magnetic field inside a solenoid is the permeability of free space times the current times the turn density. So we can get the magnetic field because we've got the permeability of free space, 4 pi times 10 to the negative 7. They told us the current was 12 amps. So here's the 12 amps. But here's where we're going to need to get a little thought. Okay, so 300 turns. And its length, and I'll call that 0.3 meters. So 0.3 meters long. So the number of turns is 300, and we are at 0.3 meters. Oh, that's just like the last problem we just did. That's a nice round 1,000, isn't it? Because 3 goes into here after we multiply both sides by 10. Yeah, so that's an even 1,000, which we could call 10 cubed, which would be nice to change that to 10 to the minus 4. Okay, so the magnetic field would be 4 pi times 10 to the negative 4, and then times 12 amps. And so we're looking at a field of 0.0151 Tesla. We might call this 15.1 millitesla. Okay, and so there's kind of the main step, if you will, Ampere's law. But it goes on to talk about the the flux. Okay, so the flux is what you get when you take the strength of the magnetic field and you add it up over the entire area. And I think what the other half of this problem is really trying to get you to focus on, it's not just flux, but that's part of it, but to also then recognize that this little formula for the magnetic field of a solenoid is only in the tunnel part of the solenoid, because outside of the solenoid is zero. And so if I did kind of a cross section here with my black marker, so if I did a cross section, and so here's the solenoid, and the disc has a much bigger radius than it, we're going to say that there's a magnetic field only in the tunnel part. And whether it comes out or in kind of depends on whether I, flipped it this way or flipped it that way. But the point is there's no magnetic field here. So when I go to do this dot product, I might mathematically say, okay, this would be the total flux through this disk, but I'm going to break it apart into two pieces. The first part is this inner part here. I'll call it area 1. And the second part I'll call area 2. And maybe it's so obvious I don't even know to point it out, but there wouldn't be any flux here. So this is 0, and it's 0 because the magnetic field is 0. And so I think a big part of this second part is, as you're calculating the flux, is to recognize, where there is and where there is not the field, so you know what area to use to calculate the amount of flux. And so we're asked for the total flux in the whole thing, but since most of it, what I called area 2, doesn't really have any flux. So I'm just really getting the flux with inside the solenoid. Or put another way, it really doesn't matter how big you make this loop on this disc on the outside, as long as it incorporates the whole solenoid, this is going to be the total. All right, and so when you do the dot product, you're going to see that the angle is 0. Again, and that's probably another part of this, is what is the direction of the magnetic field. And so the magnetic field is either coming out or in, depending on how you imagine my cross-section, this way and this way. And I didn't make a distinction purposely, just so that I could say that that angle is 0 and that it's uniform with inside of the solenoid. And so you ultimately just end up with the area of the solenoid. And so there's no angle to worry about, and there's no little variations that need an integration to do. And so it's just B times A. So it's the simplest flux calculation. But we got to justify it to get there. Okay, so the magnetic field, which we did earlier, was 0.0151 Tesla. And the area of this solenoid, well, we better jump back to the problem. The solenoid has we wrote here, radius, and that's in centimeters. So its area would be pi times 0.0125 meters squared. Whole thing squared, the meters squared and the radius. Oh, just that part squared. Okay, so pi r squared. And so now grabbing my calculator, 0.0151 for the magnetic field, times the pi, and then times the 0.0125 squared should give me an answer of 7.41 times 10 to the negative 6. And I don't think I really emphasized this, but a Tesla times a square meter is called a Weber. And as we get into our circuits, we're going to talk more about Webers, but not too much, actually. So I'll just call it for what it is, but there it is, that many Webers. All right, well, this is a good stopping part because it took me 50 minutes just to do these 3 examples, and hopefully they were helpful to someone. I'll throw out those other 3 after maybe I take a break and get a bite to eat and come back. All right, take care.